Power electronics and motor drives. Hello everyone, my name is Rafael. I'm an electrical engineer, and in this video I would like to speak with you about the power electronics and motor drives, and to do so I'm bringing this exercise. It is basically a three-phase motor driven by a frequency inverter whose power circuit is connected to the 60 Hz grid, and the control circuit connected to a power electronics element. There are some details here that we need to understand. I am going to read the exercise for you to get it all. The following figure illustrates a three-phase induction motor driven by a frequency inverter whose input is connected to the grid with a constant frequency equal to 60 Hz. By varying the reference current from 4 to 20 milliamperes, the motor speed of rotation varies linearly from 0 to 2000 RPM. The reference current comes from an analog circuit with operational amplifiers in the inverter and voltage current converter configurations. The inverter amplifiers input the inverter amplifier input is connected to a constant voltage source of 1 volt here. Okay, now the question: calculate the resistance of the potentiometer that will drive the motor to 1000 RPM. Okay, this is the question, and this is exactly what we are going to do. First of all, we need to write a graph here that will represent the variation of velocity, speed of rotation, as the reference current is varied. So I'm going to have here a reference current in milliamperes. Okay, it begins in 4, okay, as the exercise said, and it finishes in 20 milliamperes. And here is 0, and here 2000. Okay, we can connect here, and we get a line here. Okay, what we want is the current Iref for a velocity of 1000. This is what the question is about. Okay, this is what the exercise wants us to calculate. First of all, we are going to see that for a linear function, f of x is equal to a times x plus b. Okay, our first point is the current equal to 4. All right, so f of x equal to 4 is going to be equal to 4 times a plus b equal to 0, okay, because here the velocity is equal to 0, okay? Then we find that b is equal to negative times 4a, negative 4 times a. And now the other point is this point 20, 2000. Okay, f of x equal to 20 is going to be equal to a times 20 plus b equal to 2000. Okay, and if we develop this, we get that a is equal to 125 and b equal to negative 500. All right, are you guys understanding everything? Then this graph here is ruled by this equation here, n equal to 125 times I minus 500. This is the linear function that describes this linear line here. All right, so with this at hand, we can calculate the current for this point here. This is what the exercise wishes us to calculate. And when we get this, we get that 1000 RPM, equal to 125 times I, okay, the current that we need. We don't yet know, but we're going to calculate minus 500, okay. We are going to simply use this equation here, and ultimately we get that the current that we're looking for is 12 milliamperes, okay. So this is the current that we are going to use here, that's going to set the motor to rotate at 1000 RPMs. Alright, are you guys comprehending everything? From this we can conclude, okay, so just remember, I'm gonna put here that I reference is equal to 12 milliamperes. I'm not going to erase this result because it is important. What I'm going to erase is here, okay, just to get some room for our next calculation. Alright, I don't want to speak fast because I want you guys to understand everything, but I don't want to make this video long, so we need to optimize our time. Okay. Alright guys, now we need to understand that this current here, the reference current, is going to pass here and go to the ground. Okay, this voltage drop here on top of this resistance here, this voltage drop can be understood as here too, okay, because in operational amplifier theory, there is a virtual short circuit between this point and this point here. So, virtually, not physically, there is a virtual short circuit here from this point to this point here. Then, you can understand that this voltage drop here that I'm calling Vk is also here, Vk. This is key to understanding this. If you cannot comprehend this, you are not going to comprehend the next step, okay? One more time. In operational amplifier theory, there is a virtual shortcut between this point and this point here. Then we can infer that this voltage drop here on top of this resistance is also on top of all these here, okay? Then if we do this, we're gonna see that this voltage drop here, Vk, is equal to 12 milliamperes times 250 ohms, and then we find that it is equal to 3 volts, okay, 3 volts. Vk here, all this is 3 volts. All right, but now what we need to do is to calculate this voltage drop here on top of the potentiometer here. The exercise already gave us that here is 1 volt. And again, knowing that there is a virtual short circuit here, not physical but virtual, then we can infer that the voltage on top of this resistor here is 1 volt. Okay? So, if here is 3 volts and here 1 volt, then if there is any current here passing in this element, okay, if there is any current passing here, then we can say that the resistance of the potentiometer is going to be equal to Vk minus Vk is all this, Vk all this, minus 1 volt. 1 volt is only here, 1 volt is only here, and Vk is all this. Then we have this plus this equal this, okay? Do you understand? This plus this is equal to all this. And then the difference between this big one and this small one is divided by 100 milliamperes, 100 microamperes. And why 100 microamperes? Sorry, I haven't yet mentioned it because this is the current that's going to pass here, okay? I jumped this step, but if you simply divide 1 volt by 10k kilo ohms, you're gonna get 100 microamperes. Okay, I did not mention this, but now I'm mentioning this. You can calculate this current by simply dividing this voltage by the resistance. And then, if you discover that the current that's going to pass here is 100 microamperes, you can get that it is going to be equal to 2 volts divided by 100 microamperes. Okay, so the resistance of the potentiometer is going to then be equal to 20 kilo ohms. Okay, so this is our final response. You are going to adjust the potentiometer to this resistance. Okay, you can do it automatically using SCADA systems, or you can have your own hand adjusting this, and then the motor is going to behave in accordance with what you want it to behave. Okay, my friends, this was the video that I wanted to make. I hope you guys enjoyed it. I'm a teacher. If you want to book a lesson with me, use my WhatsApp number, guys. Goodbye.